Hey guys, so today I'm going to be going over some simple explanation about solving force vectors and how you can really start to conceptualize these when you're doing some statics physics equations. So a force vector is just the representation of an applied force in a specific direction with a magnitude. These are what vectors are, and you should already start to have a bit of a grasp about how you can picture a vector in 3D space. So let's take, for example, this is our XYZ axis. This is our coordinate system, and so we have a point at point O to point A. You can picture this as like a rope. Like this is just like a wire with some amount of tension. You can have it be pulling on some surface. It doesn't really matter, but let's just say this is our rope, right? It's pulling onto something. And so there's going to be a tension force acting in this direction because there's an item here and then something is pulling on this rope. We don't know what that force is, but we know that the force is going to be acting in this direction. And we know that it's acting along point O to A, and so we're creating a force vector in this general direction. The first thing that we want to do to solve this is we're going to go about solving for what that actual position vector is. And so our position vector we can represent as RAB, or ROA, sorry. So ROA. And so this is telling us that it's the position describing what that point is. So like from O to A. The way we would go about solving this is we would actually just use some simple subtraction between the endpoints. So we would get ROA, the vector of that would be it would be like the x position minus the y position. So you would do like the x of A minus the x of O. And then that would be like your first one. That would be your I value. So that would be your I value plus your y of A minus your y of O. That would be your J value. And then you would do the same for your K value. If I have space, I'll put it on the board, but yeah. So you do, so this is how you would very simply go about solving for your position vector. The second thing that you're going to want to do is you're going to want to solve for what the distance of that actual value is. And that's pretty straightforward because now we have a position vector. The distance is just the magnitude of that position vector. So we can solve for that by doing this, by taking the magnitude of that position vector. And as we know, the magnitude is just the sum of those values, but all of them squared under a square root. So that would be your I, J, K values all squared. You could write that out, but it would just be whatever your x is. So your XOA squared plus so on for your y and for your z all squared. That's like the magnitude. And then so now that we have this, we can actually create a unit vector. A unit vector is really important because it just purely tells us what direction we're acting in. And so a unit vector is really helpful because we can multiply it by the force. And we'll get to that in a second. But first, I just want to put the basic on the board. So the unit vector for position OA is going to be equal to like this. Okay, so what we'll see how is, so we take our position vector, we divide it by the magnitude, and then we get a unit vector. And so this is very important because with this, we're able to do something very, very interesting. And I'll show you what that is. Sorry about that. Oof, okay. Let's move over here now. Let's get a little bit more space going. This is our first step. We'll call this step 1. This is solving for the position vector. Very important thing you need to know now is now that we have a position vector and a unit vector describing where that force is acting, we're going to go on to step 2. Step 2 is now multiplying the force that we have in that direction. So let's say, for example, we have a force with some arbitrary value. For now, let's just call it a force. So we could give force like 200 newtons, but for now it's just force F. But this is a magnitude. This doesn't describe where the force is acting on. And so for a magnitude, for a vector force, what we need is we need a force multiplied by a direction. And that's what our unit vector is really telling us. Our unit vector is saying, hey, so like I'm about to punch you, but I don't know where to punch. So the unit vector is telling us the direction that we're actually punching in, and the force component is telling us how strong we're punching. And so when we perform this, we get our actual force vector. And so now that you can see, it's actually really simple to go about solving this because we have our unit vector. All we need to do is just do the dot product multiplied by some scalar. That's where our force value is. And so let's say, for example, you have a unit vector that's something like 2i plus 3j plus 1k. So with this, if our force value is 200 newtons, then literally all we would need to do is just go, okay, so then so force times UOA is just going to be 2 times 200, boom, 400 newtons. I don't need to write it there, but 200I plus, and then boom, 600J, and you get the point, 200K. Running out of space. But really, the reason why this is so valuable is because now we're starting to understand that we're acting with magnitude in a certain direction. And that's kind of the gist of what we're solving for here. But yeah, that's kind of the basic of it. Now, we're going to go into components and how we can actually go about solving for the component acting in a direction. This was kind of an introduction into the very first step. Now we want to consider what it actually means, right? So let's kind of draw this on our graph a bit better so you can start to understand visually what's happening. So if this is our position vector, right, we know that our overall force, like our force vector, is acting in this direction. Let me make that a bit bigger. Our force vector, is that bad? A bit small. Anyways, our force vector is acting in that direction. And so our unit vector is over here. That's our unit vector. Okay? Unit OA. And that's kind of telling us where it's acting, and then we have a magnitude of that force, and that's what we start to do with it. Okay. So now that we have that, we can start to understand how component vectors will work. Let's redraw this because I want to actually make it a little bit bigger so you can see better. Let's say here. Okay, good. So if we have a specific value, let's say for example we have a force vector that's acting along this plane. Okay, but we have another force that's acting in this direction. Okay. We have a force vector that's acting in this direction. This is kind of perfectly lines up, so let me fix that. So how would we go about solving what amount of this vector is acting in this one? Well, what that means is we want to solve for like what component of this section acts on here. And so if we're trying to solve the component, we want to know how much of this force is acting in this direction. To do that, if you've learned from linear algebra, that is just going to be your dot product. And so you can kind of represent it like this in a way, right, where this is like a right angle triangle. It's a bit confusing because it's in 3D space, but all you need to understand is that what we're doing is we are taking this vector, A, and we are projecting it on to our vector, B. The reason why it's called projection is because you can imagine literally as like, it's like a projector that you're dropping onto the vector beneath. And so what you're doing essentially is you're trying to figure out how much is acting in that direction. How much of A is acting in B? Well, if we think about it, this component, this is what's acting in the direction of B. If you need to understand that a bit more and you're confused about that, I might make some more videos on that, but ultimately I'd probably recommend just searching up vector projection, and there's better ways that you can go about thinking of that. Okay, so what we would do in this case, very straightforward, is we would just say, now given this, we would just have to go and say that our A times B is equal to this section. So we can label this as something like, we can call this component over here, we can call this section, we can call this some resultant value r, and so A times B is r. And that's as straightforward as it gets.